Ladies and gentlemen, good afternoon. My name is Nikolai Chernavin, and today I am presenting our work on the ensemble of linear separators, an universal and interpretable classifier. Why are we doing this? In modern AI, we have reached a paradox. Our models have become extremely powerful but increasingly opaque. When algorithms make credit decisions, medical diagnoses, or fraud alerts, we can't rely on post-hoc explanations of black boxes. They are often misleading or inconsistent. That's why there is growing interpretable first movement in machine learning, advocating models that are transparent by design, not retrofitted with explanation afterward. Our work belongs exactly to this category. The core idea behind our method is simple but elegant. We use k hyperplanes, each with unique voting weight equal to power of 2. For example, 1, 2, 4, 8, and so on. Each hyperplane casts a yes or no vote for every observation. The sum of these votes define an unique region ID, and each region is then assigned to a certain class. This gives a single interpretable rule that works for both binary and multi-class classification. What's new in our method in comparison with committee machines? Historically, ensemble or committee methods like anonymity, majority, or seniority committees combined several linear classifiers to make joint decisions. But these classic approaches had major challenges. They often lacked strict interpretability. You could see the votes but not easily understand the rule. It was unclear how many committee members to include. Too few and you lose accuracy, too many and you lose meaning. In our method we compress all this logic. Each hyperplane has a binary weight, 1, 2, 4, and so on, meaning every possible combination produces a unique integer code. That code identifies a region in the future space, and we simply assign to those codes two classes. So, instead of a fuzzy ensemble, we get a compact and human-readable decision rule. Each region corresponds to exactly one class, and every decision can be traced back to the specific hyperplane that voted for it. Let's visualize what's happening geometrically. Imagine the future space sliced by several lines, or hyperplanes in higher dimensions. Each point in the dataset lies somewhere relative to the hyperplanes, above some or below others. We translate that geometric position into a number, the sum of active binary weights. Because powers of 2 are unique, every combination of hyperplanes corresponds to a distinct region up to the power of 2 region in total. Then classification becomes simple. Region number 0 might correspond to class A, region number 5 to class B, and region number 6 to class C, for example. It's an elegant blend of geometry and arithmetic. Every point gets a digital address in the space, and that address defines its class. If looking in our model, formally the ensemble of linear separation is a mixed integer linear program, or MIP. A variable encodes whether each observation lies above or below each hyperplane. Constraints ensure that no two classes share the same region IDs, and the objective may be different. In our article we studied two types of objective function, either objective minimization of total misclassification magnitude, like is shown on this slide, and we can also make minimization simply by counting the number of wrong points. Also shown the example of model in these slides. This structure brings several benefits. It's mathematically rigorous. You know exactly what the model optimizes. It's auditable. Every constraint and variable has meaning. It's extendable. You can add regulatory or equality related constraints. For example, in credit scoring, you can enforce monotonicity, ensuring that a higher income never leads to a worse score, simply by adding linear constraints. That's what we mean by formalizability. ELS isn't just a model. It's a framework that can adapt to rules, ethic, or domain logic. Studying making comparison of our model with other methods, we studied such methods as softmax, random forest, gradient boosting, and knot. And we studied them on some quite simple problems in UC machine learning repository like iris, wine, seed, zoo, and soybean. It's quite simple classification tasks, and all models showed nearly perfect accuracy on these small datasets. So we focused our studying on training time and interpretability. And here's what we found. ELS was orders of magnitude slower than other algorithms, sometimes hundreds or even thousands times slower, but it produced explicit transparent rules that could be reviewed, audited, or even implemented manually. So while gradient boosting or neural ensembles give speed, ELS gives us trust, a model you can actually inspect and verify. So in practice, where we can use our method. So actually, first of all, model risk management and auditing can be a perfect area to use such models, because each class is linked to a set of region IDs. You can build a simple checklist, like if the point is in region 3, 5, or 7, it belongs to class A, as example. This can be directly verified by regulators or risk officers. Second, it is perfect to use it in some small or medium scale problems, because such model can be a good reference or benchmark model to validate that more complex models like neural networks behave consistently. And third, such models is good for education and research, because it based on linear programming. It helps visualize how geometric separation and optimizations interact with each other. It's a perfect teaching model for students exploring the boundaries between classic geometry and modern ML. Talking more about what limitations our problem what limitations can be in our methods. First of all, we said about speed and scalability. Training can be several orders of magnitude slower than classical algorithms. ELS solves an optimization problems, not a heuristic, so it pays for precision with time. So also, exponential region growth can be serious problem. The number of possible region growth is 2 to the power of x of k. That means the choice of k the number of hyperplanes is crucial. Too few and you can't separate classes. Too many and computation explodes. And you can also have some problem with numerical stability because we use some constants like L and epsilon, and it's basically use heuristics methods to choose value for them, and so if you use too large or too small, you can get unstable or incorrect solutions. So thank you for attention.